Okay, so we mentioned the impulse momentum theorem. People pretty much kind of know the statement of it, but should be able to derive it to be sure. But there we have it, right? And this is average force, but of course, yeah, that's going to work because your force over that hour of time is not going to remain constant, okay? You don't really have a very constant 1/10 of a meter per second, but in an hour, 1/10 of a meter, so what's the average, okay? 1/10 of a meter, 1/10 of an inch per second, right? Or per hour. Okay, so we've got information about the force. We've got some information that is probably related to a time interval, okay? We've got some information about velocity. What information do we have about velocity?
We know it's change in velocity.
Well, we know what the change in speed is, right? From 8 meters per second to 0, because the water hits and pretty much stops. As I said, there are little splashes that go up that might amount to an extra 1%. Okay? But we're just going to assume, for the simplest model, that the rain hits and stops, right? So the change in speed is 8 meters per second, right? And I haven't said velocity. Why haven't I said velocity? Because we haven't yet set up the conditions of the problem, which means choosing a coordinate system, right? Now we're going to assume that the rain's falling straight down, okay? It's kind of implicit, and that's kind of the way it is outside right now. There's no significant wind, okay? So we want the average force. We know something about time, hopefully. That would be 0.1 inch per hour, whatever that relates to when we pull it into here, and we haven't talked about that part yet. But we might want to look at what happens in an hour, right? And then we'll have a delta t. Okay? Now, speed. So what's delta v? You can't tell me until you tell me the direction of your coordinate system. We only need one dimension because everything's just moving along one dimension, right? Okay? What's our coordinate system going to be?
Down is positive.
Okay, so a single axis. With downward positive, right? You could have chosen upward positive. It's kind of natural, but since everything's moving downward, it's probably better to choose downward, right? So, initial velocity is 8 meters per second. Final velocity is 0 meters per second. And delta V equals -8 meters per second. So there's what we know about velocities, right? That's going to be very relevant because your delta mv is really m delta v plus v delta m. It's a product rule, just like in calculus. Okay? And since the mass of the water doesn't change from hitting the roof to after hitting the roof, there's no delta m, so it's just m delta v. I'll talk about that a little bit. Okay? But the change in mv in this case is just going to be m times delta v. Okay? That's all you really need to worry about right now. Okay, so seems like we got a lot of stuff here. Okay? Any preference for what you want to use for delta t? Use a second, minute, microsecond, year?
Second.
Okay, could be second. Okay? Is delta t equals 1 second. Okay? And that's actually going to be kind of convenient because now we want to know what to use for the mass. So, how are we going to get a mass?